Okay, so it's my pleasure to welcome Matthieu for the seminar in the context of the PhD defense of Clément Romac today. Matthieu is one of the key researchers in AI in the AI department at Sorbonne University, as well as director of Valeo.ai, showing both very interesting fundamental research, in particular on the multimodality in AI models, as well as application in real world context. For example, in the domain of cars. I don't know if you will talk about this dimension today,
No.
but everything
We can.
everything you do is
Yeah.
interesting to us. So feel free to
Okay.
discuss whatever you want. Do you prefer questions at the end?
No, up to you. Up to you if you
Okay.
want. Please
So it's
interrupt me,
questions.
ask question. Okay. Ouais. So thank you very much. It's my pleasure to be here. And so for today, I'm going to present you, at least two works that we did with my team at Sorbonne. So in that case, is a joint work with postdoc Jenny Parek and Arnaud Daponi, and also PhD student Pekka Hayatan and Mustafa Sukor, and also a colleague Alistair Newson. And so in this work, so we try to analyze, somehow, multimodal LLMs, or let's say multimodal models, and to see what's going on inside. And so that's why I call analyzing. But for sure, when we talk about analyzing, it can be interpretation, it can be explainability, it can be monitoring, different things like that. And in my case, I'm going to really, to show something about explainability and something about controlling. So let's say steering, for this kind of models. Okay. All right. Okay. So, want to give me the screen. Okay. 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 Okay, all right. Okay, so for the kind of multimodal system we are talking about, when I say multimodal, so I'm guy from computer vision, so this is just to go out of the text and to start to have as well as input, that can be images, video, or even audio, or other kind of things 3D data, 3D points, meshes, and whatever, as well for the input as the output. I would say so, one of the most, certainly multimodal model have been proposed recently by our colleagues from EPFL, from Amir Zamir team, in collaboration with Apple, and is about really, in that case, being able to process as well as input or output, things like depth, normals, or RGB, of course. But also, some kind of, to put as input, some kind of clip features, and then to be able to have some, at the output, of course, caption, but that can be also ages, whatever you want, segmentation, or even, more tricky things, right? And of course, in the middle of all of this, there is this kind of embedding, so let's say encoding, for each of that can be shared or not, for each of the modality, and of course, something that is likely, a decoding, and now, most of these things are based on transformer blocks, right? Okay, so for today, I'm just talking about this kind of, so sometimes it's called VLM for vision language model, or LMM for large multimodal models, or multimodal LLMs in our case. But it's more or less, the idea is to put together, image plus textual query or something like that at the beginning. Okay, so this kind of vision encoder plus a big LLM decoder, okay, that can, of course, have as input as well, the visual information, as well, some textual token, and then producing at the end, the kind of generation is always, language, right? Okay, and so on the, let's say, perceptual or visual side, you have this kind of big encoding, big, or you prefer encoder that you can take a clip or you can take a VIT or whatever. And on the other side, I mean, like it's a kind of big LLM. Usually, I mean, like both of them maybe stay frozen during all the pipeline of the learning or the adaptation. Sometimes there are still, I mean, like some kind of fine-tuning mechanism that we do like now. But the main part is, of course, is to map together. I mean, like this kind of a part of this input, and the input can be caption this image plus one image, and so one of the most important things in between, I mean, vision and language is how you can map the somehow perceptual visual information into the big LLM, right? And so, I mean, like we did a lot of work on that, trying to say, okay, take your, really, I mean, like take your llama, take your whatever the kind of big LLM you have. I mean, like just open source things here, and then how we can plug and learn for, I mean, like only few millions of parameters somewhere in between, and then you have perfectly, I mean, like multimodal model working on whatever you want, and so the idea, and we did a lot of things on that, is that after 1 hour of just fine-tuning of, so training and fine-tuning of this part, you are able to apply to any kind of use case you have with dedicated images plus dedicated task or question that you can have. Right, and of course, I mean, like still have the question, or where do you put? I mean, like the connection is something that is how you map them together. I mean, from the top, or you can extract also from different layer here. And after, are you coming? I mean, like to prepend. I mean, like saying like when you do these things, and I do like to say that first, actually, what you did is that you just translate. I mean, like your image in a book, okay, and you give this book at the very beginning as a context, okay. It's really, you prepare all the feature before the query. They're very simple, and in that case, we know that we are going to benefit of the huge ability of the LLM to understand a big context like that, a big token-based, textual-based context, okay. But of course, I mean, like the other way, I mean, like, is not to put everything at the input. I mean, like, exactly as it was textual token at the input, but to go through, I mean, directly this kind of cross correlation. I mean, like, so to go enter the big LLM at different layer inside. And we know that this kind of things is really, I mean, like mimicking. So more the second option that I show you here is really mimicking, I mean, like the seminal work of Bashwani and colleague about translating from one language to another, where it's a pure, I mean, like for the second language like that, then the output, the pure decoding, I mean, like coming with this kind of cross attention. Okay. Okay. So this is just to give, I mean, like the big picture of the kind of model we are talking about today. And if you see, I mean, like when exactly, I mean, this kind of model starts is certainly with the Flamingo, and I say to Pierre-Yves, I mean, like we had a very nice collaboration with Ginface with this kind of system that is, I mean, like a kind of, I mean, like open source big model. And in that case, train from scratch. Okay, so we really want to do, or let's say, train from scratch or fine tune at a very high level. I mean, like for all of that. Exactly as the Flamingo. So Flamingo come with cross attention. So Flamingo was the model of DeepMind doing that. And in Obelix, Idefix, we really, I mean, like analyze what was the best strategy. And finally, as colleagues from other team like Lava or now Quen, I mean, the idea is really, I mean, like to put everything at the beginning. Okay, and so in that case, it was, I mean, certainly the most complicated things. It was how to get a very large data set, okay, open. And so it was a huge engineering work. I mean, like to be able to crawl all the web and to filter all the data and to keep enough interleaved image plus text information on at scale. Okay. Okay, all right. But okay, so for today, let's imagine that it's already ready. I mean, like it's been trained, huge amount of data, blah blah, etc. And so I just summarize in this big picture how it works. Now your system is trained, and now you want to start a kind of analysis. Okay. So you see perceptual is this big part, the mapping is here. Then, okay, you go through the big LLM, and this kind of LLM is always, I mean, this kind of self-attention, FFN, and so on. Everything is residual. And on top of that, okay, you have this kind of course, autoregressive structure, I mean, like for the decoding. Okay. And so, as I said in the first part, we try to explain something about that or to see how it works inside, and can we do some analysis? I mean, like if we open, I mean, like all the different layer and to see in which layer. So somehow it's a latent space, and we want to be able to say how the data are going through. I mean, like this latent space, right? And so what we did is that we say, okay. We don't want to explain in general, but we want to say, okay, give me a data set, give me a topic, and let me see if I can say something about that topic, what I see appearing, emerging inside my LLM. I mean, again, through the data, through the data passing here. Okay, so you can imagine that, let's say, for instance, captioning. So you have a lot of example, okay, with their caption, and we are going to take one token of interest that can be, for instance, give me everything about train that you see in that data set, okay? Or dog or cat or whatever. And typically, I mean, if I say train, what I expect as output is that, okay, can you tell me that when I put every data inside and I go into a certain layer, is it able to, is it possible, sorry, to extract somehow some cluster or some concept that are meaningful inside this space? And the kind of result, I'm going to detail how to obtain that, but it's just like to show you what we want to do, is that to be able to say everything about train have been maybe, I mean, like group or cluster into a different here concept, and each of these concepts are multimodal. That's why it's interesting and different from before, as well for images or for text, is that means that the kind of concept we are pointing here may be explained as a text output or a few words that are the most representative of this part of the space. But also, I mean, like to be able to say, and this kind of images are the most related to this concept also. Okay. And so you see, I mean, like you have, for instance, for trend, you see that you have a lot of bridges, I mean, like images with bridges, etc. Or you have very historic, I mean, like kind of old kind of train, or you have many things about railway station, or you see appear, and so, I mean, different kind, for instance, of train that can be here, for instance, electric train only. Okay. So how to do that? I mean, like very simply, we take, as I said, I mean, like okay, our images going through that, going and passing through the LLM. Okay, and so we compute everything like that. The textual token also here coming from the query, and after we start to generate or to put the question. I mean, like teacher forcing or as you want. Okay. And the idea is that for each of them, okay, if it's related to dog, we can take one vector for each of them. Okay, that represents, summarize, that can be the last one or a mean, it doesn't matter actually. You take this vector and you can do it, I mean, like for all the relevant set of images inside your big set, so that just talk about train in that case. Okay, so you have a subset with representation. Each of them, it's one vector. Then you have a big matrix of that. And we are going to do a basic clustering, okay, and of this matrix. Okay. So it's just to see how we can decompose this matrix into of course, the concept dictionary on one side, okay, plus the concept, I mean, multiplied by the concept activation. So this is a very classical problem of decomposition, matrix decomposition. you can choose whatever you want here, or even you can imagine to have just a clustering, k-means or something like that. Huh? But in that case, what is cool is that by having, I mean, like the V, so deactivation that you just force to be non-negative, I mean, like the idea is that each of the Z vector may be decomposed in a sum over, I mean, the V decomposition that are all positive. So that means you activate some of the cluster to be able to represent correctly, I mean, like each of these Z. Okay. So there is no somehow repulsion if you have negative value. No, it's only a positive one. The most important thing is to say, I mean, like, let's say the most activating here, let's say if it's U1, and you want just to summarize, you say, okay, this vector is related to this cluster and it's over. Okay, something like that. Okay, and we do force, typically, I mean, like to have not too many, I mean, it's this kind of L1 regularization that, you know, that is pushing, I mean, like the things to be as sparse as possible. So very few of the cluster will be activated for each of the Z value. Okay, so then when you have that, okay, I mean, it's done. The work is done. I mean, you just have to see what is going down from that, because each of the this cluster, okay, the center of this cluster, so this vector that are, I mean, like, let's say the concept word, okay, from the dictionary, each of them, you can go through the output, I mean, so on that, and let's say select the top 5, the top whatever you want, that are the most probable word explaining, I mean, like this concept. One thing here. Of course, if you are not at the very end level, you still have some confusion by using, I mean, like an embed matrix on top. You can have some adaptation. Some people do some kind of lens, I mean, like to be able to do that. But coarsely speaking, you are able to, for each of these clusters, to extract, I mean, the most representative word on one side. And also, as I said, with this kind of VK value here, if you get the most, the highest value here, okay, from the dataset that you use, images, the dataset that you use to do all the analysis, what you know is that you can extract the most activating. Okay, the highest value here, let's say the three highest value, if they are coming with these three different picture images that have been used, I mean, during the building process of this big matrix analysis. Okay, so okay, just by doing this kind of thing inside the model, on your multimodal data set, you are able to extract this kind of things. All right? Okay, so for dogs, for instance, we said, okay, give me 20 clusters. Okay, so you have to fix the number of clusters in your analysis. And after you can say, okay, this is more or less all the clusters and how they are, I find by doing this analysis on my multimodal models. Okay, so it tells you two things. It tells you something about the data set, and it tells you, of course, something about the model that you try to analyze. Okay, each of them have some specificities about their latent spaces. All right. Okay. So let's say you see, and what kind of let's say use we can do? I mean, like we can use these things to analyze the data set or to say something different than just captioning. So you give me an image and I can tell you, oh, this is like puppy. This is a very small one, a cute dog that you show me, or this is a very fluffy one. I mean, if your image is close to that ones, or you can say in your data set, there are a lot of dark dogs, or let's see, I mean, you see the kind of things that emerge, and it's a kind of analysis at the macro level, or if you prefer, about the image you want to be able to give extra comments, not just captioning, typically. And what we also noticed that could be interesting is that some extra characteristic, not only about, for instance, the feature of the dog, the size of the dog, and the kind of things, but also the action. I mean, like typically there are a lot of dog running, jumping, or things like that into the grass. Okay, so we see emerging, I mean, these kind of things. Or about the different type of, you know, when you have a dog, sometimes you have a lot of sheep or things like that, and you see that it's related to this type of work for the dog, or you can see that sometimes you have a lot of relationship with cats, and this is also inside the data set. And of course, I mean, like some perhaps more unexpected things, but there is a lot of hot dog picture also in your data set. Okay. All right, and so as I said, you can do it. I mean, like for train, you can do it for cat, you can do it for dog, whatever you want. I mean, you just say, okay, I have a token of interest, and I want to see what's going on that topic and how the images and plus the text maybe. I mean, like cluster together. It's exactly the kind of things that you can do. Okay. Okay, so this is first thing, and also, I mean, like, as I said, if you come with a new image, that was, I mean, just analyzing the data set by itself, the clustering and the way that these clusters are coming and so on. And the other thing is as I say, is, okay, now I have a new image. I want to know how this image, for instance, maybe, I mean, like, compared to all the images you already have in your data set, about, it's also a dog, but tell me something about my dog. And as I say, I can tell you, I mean, like a picture, yeah, it's a lovely dog, blah, blah, blah. Okay, so you can comment, you can do the caption, and ask the system to give you the caption, but you can also have this extra information available in that case, and just to explain how you are, for instance, that seems that your dog is very fluffy, and look at that, it's very similar to this kind of dog, or your cat here, or for instance, your bus here, you can say, okay, this is, for instance, city bus. Okay, this is clearly a city bus, and I discover other like that, and so, you know, it's extra information that you can give to whatever the input you want to have after. Okay. Voilà. Okay, so this is the first step. That was just, I mean, like, to be able to go through the model, to get finally some points inside the latent space, and to analyze all the points that you have. So a kind of cluster of points, and try to find the different cluster in this, the clustering into that space. A second question that I mean, because as I said, this is more related to finally to the data. But of course, it is related to the multimodal LLM that I use for that data, because this is exactly the latent space of this multimodal model that I use to be able to do my clustering and so on. So it's a characterization, of course, of your data set, etc., what is going on that topic, but also of what the multimodal model have been trained on, and what is inside, I mean, and what kind of latent space has this multimodal model. For instance, if I take the idFix one, do I have the same cluster that if I take a Lava one, or if I take a Quen today? Okay, so I can try to say, okay, give me the same data set, different multimodal model trained on their own, right? And then, okay, may I compare how they analyze, I mean, the same data set, all right? So we didn't do that with Mulmu versus Quen, but what we did is we say, okay, we have one multimodal model doing a clustering, and then I'm going to fine-tune with a specific data set this multimodal model, and then I get another one, so a second multimodal model. And then I say, okay, this is more or less, this is exactly the same, except that I fine-tune a little bit, not necessarily too much. I mean, like on a new data set, my initial multimodal model, okay? And then the point is that if I redo my clustering and I try to compare the different clusters, may I say something about what's going on, right? Okay. And what is clear is that, of course, your second model is going to be colored by the kind of fine-tuning, the kind of data that you use, I mean, like during the fine-tuning. And for instance, we use a data set here for the fine-tuning that is going to give a lot of information about the location. Each time you have one image, this is here, this is the school, this is on the beach, this is, etc. Okay? And so what we notice is that when we redo this kind of clustering by itself, we really see that inside the concept emerge a lot, much more about this kind of things, okay? About, again, the term about location, where it is, and to have different clusters that represent different location. Okay. All right. Okay. So we can say many things, but what could be interesting is that somehow, I mean, like generally speaking, the data set that you use for the fine tuning maybe somehow discover or rediscover or understand or you can retro engineering, I mean, like your multimodal model. When you try to compare with an initial one that you have, this one, you don't know which data it has been fine-tuned. But you can try by doing this kind of analysis to see, I mean, so certainly there were some data here in the data set that used for fine-tuning that was not inside the first one. Okay. One way to see that, for instance, is to say, okay, I do my clustering here. I try to match the cluster with the new one, the blue one here. Okay. And when I see that some of them disappear, okay, so some of the cluster you see don't appear, are not anymore in the new configuration, a new one emerge. Okay. And so you can imagine that this kind of cluster may be, for instance, about something that was never, I mean, like in the first one, but very well documented in the second one. Okay. So perhaps this kind of things can tell you something about the data set used for fine tuning. Okay. And of course, this can be very interesting to know if you don't have access to this data, if this data, for instance, was secure enough, safe enough, etc. Okay. So this is one thing. Another thing that interested us was to say, okay, can I do exactly, I mean, like this mapping? So if I don't want to redo, I mean, like all the clustering, may I, let's say, may I predict what are the clusters from the first one, except for the one that, of course, disappear or appear. But most of the clusters are there, I mean, predictable, and how? So how they change in between the different. And what we investigated, I mean, like, and the results are quite positive, is that if you go by cluster linearly, okay, so you try to have some kind of linear shift inside each cluster, but of course, this linear shift is not the same from one cluster to the other. So at the end, the global change is not linear at all. But if you just respect or try to find this kind of linearity inside each of the cluster of the first decomposition, it works very well. I mean, like to be able to recover, I mean, like most of the clusters that you have in the second part, except again, what the one that will disappear or appear. Okay. And so what does it say? I mean, in kind of generality, it's a kind of representation efficient fine-tuning versus parameter efficient fine-tuning. So all the kind of path are the way that you are going to do the fine-tuning of one model. You know, now we are using, I mean, like we are not fine-tuning all the parameters, but we have this kind of LoRa things, or I mean, or other kind of adapter that you can have that are very few in comparison to offer the whole number of parameters. And this is parameter fine efficient as much as possible. I mean, like to do this kind of function. If you don't want to do that, but you want to be able to act more or less at that one, what you can do, of course, is to keep that one plus somehow some shift, right? And this is really, I mean, like the steering and or the representation, and that's why that now you work, so you fine-tune the representation directly by having this kind, acting this kind of direction that you can do linearly for all or linearly per cluster, etc. Okay. All right. Voilà. Okay. So this is more or less, I mean, like for the first part of this kind of analysis, and that just at the end give me, I mean, like the transition to go on this kind of steering, c'est-à-dire pushing some representation. Yeah. Hmm?
So you need different clusters, but do you need the data set or do you need the
Yes.
weights of the model?
No.
Okay.
No, the main idea is to have the data set to do the analysis. And so I didn't detail, but here is exactly for each of the sample, what you can do is that you have, yes, you have the model also. For the analysis to see if it works and you can compare, you need to also to have that model. but you don't need necessarily to, what we want to here to show is that we can avoid to do the clustering again here, but we can mimic the clustering by saying, okay, each of the dog data that I have, okay, I can go through that model, I have one point here, and go through that model, and I have another second point, and I can, what I'm going to use is that in which cluster this model have been used, okay, so it's, and then I'm going to take the difference for that data in that model from here to here, and I do it for all the data by just looking on that clustering. Okay, so this is really, I mean, like that. My sum here, and let's say I group the data thanks to my initial clustering, and I do the mean per cluster. Okay. Voila. And of course, after you can do many different things. If you see that one of the data is not going through, I mean, like the same direction as the other, is exactly, I mean, one data that certainly do not move at most of them, and that can be in another direction. And of course, that will explain how you can have some of the data that are not going into any of the first one. Huh? Okay. But yeah, this is exactly. Okay, so but that's true that it's interesting is that you can have the same data set and two different models, and you try to see how it moves, or you can also have only one model and two different data sets and try to see how they are changing this data set, what is different in between these two data sets. So it's the other way, the reverse way, I mean, to do some kind of analysis also. Okay. All right. Okay. And so, this second paper is related to also the same team. I think. I mean, like with Jenny at the Common. I mean, like about steering. So when we are talking about representation steering, is really, I mean, like let's say latent representation, internal or latent representation, and we try to enforce some behavior in that representation. I mean, or just to avoid some other kind of representation. Okay, that can be, I mean, like, okay, shortly noted as here, and this is actually a very old problem. I mean, like we know that, I mean, 30 years ago when we tried to work on autoencoder and these kind of things, we tried to find a latent representation where everything was linear. I mean, like this is typically, I mean, like steering, linear steering for all the things. It was very cool, I mean, like to have this kind of thing, because that means that you are able to move in between two images linearly. But of course, we know that in the RGB space, it's not linear at all. I mean, when we want to change from one image to another, but if we can go into a latent space where we can move linearly and come back to the RGB space and to see something that is meaningful in terms of transformation, we are very happy. Okay. So that's why already true for all the things about autoencoding and variational autoencoder and things like that. And then after with the pure generative model, I mean, like from images, let's say the GAN at the beginning, pure generators. I mean, from let's say from Gaussian noise to RGB images. The idea is somewhere in between, with the style GAN typically. I mean, like there are some intermediate space that we call also latent space of this GAN. And inside this latent space, we try to find some direction. And for instance, is it possible to find a direction that tell me, I mean, like I am younger or older or something like that? Okay. And so there are plenty of ways to do that. You can train SVM, binary SVM for images that you know that are very old and young, and to find a boundary like that, and to find the hyperplane that will acting as at the right direction to be older or younger. And then after you can apply this kind of transformation steering, I mean, inside the latent vector, and to get, of course, this kind of age or smile. It can do for whatever the feature you want to activate or not inside your model. Okay, so a kind of pleasant result, but okay, it's more about fun. But of course, I mean, like this question of can we steer? I mean, like also the kind of big MLLM that I just presented before. I've been, of course, even before exploring the LLM, because it's the same with the LLM. May I move a little bit, I mean, like the direction inside my LLM and having, I mean, some kind of typically safe result or things like that. It could be very interesting. And again, can we do the same thing, not for a pure LLM, but with a multimodal LLM? And so it's what we try to do. And one of the characteristics also is that, of course, if you come, you don't have to anymore fine-tune your model or for having like one model fine-tuned per kind of steering. Then you can just act if you find the right direction you want to activate on top of one model. Okay. And of course, I mean, this kind of things have excited a lot. I mean, like the community in particular, I mean, like to be able to improve, I mean, like the behavior of the model to align with human preferences and so on. So to limit, I mean, like toxicity, to limit, I mean, like, of course, harmful answer. Well, for images, I will show you, I mean, like some result about hallucination and also to really limit, I mean, the kind of visual hallucination of this system when we are talking about visual caption, right? Okay, and so again, the basic thing that the people try to do is to say, okay, you want to limit, I mean, like this kind of harmful answer. Give me some harmful answer on many, I mean, like different type of queries. You find the same thing with a safe answer and so on, and then you try to find, I mean, the right way to go in that direction. So to always go from that to that way. You try to extract this kind of big steering vector, and this is the first thing to do when you want to limit, I mean, like, or you try to limit or to correct this kind of problem, right? As I say already, I mean, like for images, we have seen that this kind of global linear changing is not good, I mean, like for MLLM. But of course, that's true also that even for this kind of LLM things, I mean, like people know if you add these kind of things, whatever the kind of question you have, I mean, you are not meaningful. I mean, like, and so if the question is how to set taxes or, for instance, health question about to consult a doctor or something or a finance expert in that case, and it just tell you everything every time. I mean, like no, I mean, like it's dangerous or something like that. It's not meaningful at all. Okay, so this is just to motivate. I mean, the last things that was already, I mean, like in the first part. That is, it's a very interesting to have some answer that are depending to the input. And that's why steering input dependent is exactly, I mean, like when I saw, I told about linear per cluster, it was already, I mean, like something that then is at least cluster dependent. And so the most critical things is input dependent. Okay. Voilà, so again, you have exactly the same model. You take, I mean, like your data. You have the output generated by your data in that case, and you have all the hidden representation, as I said before. And here I put the L for the layer, and the position is where you are in the generation, into the generation of the question or after the question also. Okay. And so the way to make the thing data dependent very easily with this kind of vector is just to add, and this is the first technique, the baseline that we can do if we want to have data dependent, is that we just add a prompt to steer, okay? And this prompt is just a way, I mean, like with this kind of positive or negative prompt, is that you add something, I mean, like add the prompt. So for each of the question or the things you have, you add something that push, I mean, something in the safe answer after, or that try to push you in unsafe, or to push the system to for instance, to answer whatever the kind of things you have. And that can be done for harmfulness or health care, advice or things like that. Okay, so there is a benchmark. We'll come back to that show different kind of behavior that are somehow not acceptable or not safe or whatever. And then for each of the this type of question, you can add a positive prompt. So you go through the positive, so that try to push you in the right way. I mean, okay, completion in that case, or you can say, okay, I redo the same thing, but with a negative add prompt completion that simulate, I mean, typically, I mean, like undesired behavior. Okay, and so you have two types of prompts. Huh? The first one, as I said, if you redo with the T minus, it will give you another direction. Huh? And let's say that this is going in the right direction. This one is not the right direction. So if you do the difference between these 2 points, you have exactly the Z, that is the direction going from not good to good direction. Okay? So this is typically, I mean, like, and of course, this is depending on the data. For each of the data, it will change, right? Okay, because this is coming after that. And so that means this vector is x-dependent, is of course dependent on the way that you do. But once you have that, you can steer, okay? And also with a weighting factor here, I mean, like your representation. So what you are going to say, I mean, like, but pushing a little bit in the good direction if you were hesitating. Okay. Voilà. So this is typically, I mean, the first things to do. But of course, there is a big limitation, and the limitation is that test time, inference time. I mean, you don't know necessarily. I mean, what type of problem you can encounter, what type of question is it, and so on. And so it can be. I mean, like it can be a problem because you don't have the topic. I mean, like or the kind of things that you really expect to have at that time. And of course, it comes with a lot of additional work, so it's not completely efficient. Okay, so instead of doing that, what you can do, and it's what we did propose. I mean, like, is to learn these steering things. Okay, and so basically, you do exactly what I showed you before, but for each time you have this Z value, all right, you get a training data set of that. I mean, with so many of the data that you have in your data set, plus this kind of things that you do, of course, during the training, you get this vector, and you try to, of course, predict this vector from your data. Okay? And so this is just to know how you are. So at this step here, okay, you know that the kind of direction adaptation you need to do in order to avoid, I mean, like doing this kind of negative answer. Okay, so it's exactly the same, huh? So except that you have the optimization. So that means after, at inference time, what you do, and it's simpler, I mean, you go through your model, from that you estimate the G values that give you, I mean, the direction, the steering direction. And this steering direction, you can inject that steering direction with your alpha parameter where you need to, I mean, like before generating, I mean, like the final answer. Right, okay. All right, and so as I said, the evaluation for that, I mean, we have two kinds of evaluation. One is for what we call safety enforcement, and the other is hallucination. And so the kind of baseline, of course, I don't do anything. You can do this kind of mean steering. There are plenty of ways, or at least two ways of doing that. Of course, we can discuss more about the parameter. The benchmark is one benchmark introduced by recently, I mean, like about safety bench. And so there is different type of harmful or illegal activities inside, at least 9, about financial elsewhere, or about harmfulness or things like that. And what they want is to have something that is not pure textual problem. I mean, like usually, I mean, like, so they try to not have, I mean, like too harmful things detecting that are detectable into the textual query. And so they put inside the image somehow some illegal information, many things, or they try to embed, I mean, also an additional things about the query that is trying to pushing, I mean, like the answer in the bad way, okay, in the bad direction, all right? Okay, so this is the kind of data set. And of course, then you need to have for the evaluation, it's a little bit tricky because it's always very simple to be not harmful at all. You never answer. Huh? You never answer. This is very cool. I mean, like, let's say the harmfulness going, I mean, it's completely safe. When you do that, I don't want to answer anymore. Whatever the question, whatever the things. Okay. So of course your unsub score is fantastic, is equal to 0, but at the meantime, the response quality is completely out also. Okay. So what I mean is that you can just have only one criterion to evaluate these kind of things. You need to, of course, to keep, let's say, response quality equal for any kind of techniques that and as high as possible, right? And to see after different things that can be harmfulness, that can be expert difference, and then you need to keep them together. Expert difference is somehow an analysis of the answer to be able to say to give you a score about how this answer will engage you to go to a doctor or to ask for advice on something like that. Okay, so there are techniques, I mean, like to do that. There are some specific models to be able to give you a score about the harmfulness, the unsafe type of answer that you give. Okay, so typically, I mean, like when you do no steering, usually you are very poor in harmfulness reduction, and you are also very poor, as I say, in the way that you can put let's say the user to ask for expert or things like that. Okay, and you expect when you are going to do learn to steer or prompt to steer to have a much more safe answer, and also, I mean, to maintain a good expert difference. That can be also, I mean, like, of course, for harmfulness, but that can come in particular. Let me show you one example. Where it is about, yes, having going to see an expert. I mean, for this kind of, I can't remember what is it, but financial advisor that can give you, I mean, like, many different things on. Okay, and then of course when you put everything together, as I said, I mean, like, if you see, I mean, like the quantitative score, this is an unsafe score that has to be very, very low. This score has to be high. And as I say, we keep, I mean, more or less at the same level of quality for any answer. And you see no steering, the mean, there is two variants of mean, the learning to steer or the prompt to steer. And so what you really try to do is that to minimize these kind of things, keeping this very high. Okay, so this is not always, I mean, like the case, in particular when you do this kind of mean, where you are usually able to come down the unsafe score, but not to keep the different score large enough. All right, and last figure, just to show another example about hallucination. So typically, hallucination is that, let me show you one example, is that, and there is a data set, and there are some more, the pop data set is the first one, certainly, I mean, like doing this kind of thing, but after there are more interesting and complex questions about the things, but this is typically, I mean, like, when you have this kind of multimodal model and you ask something about the image, right? Usually, whatever the system, they answer. So if you ask, is there something, it will tell you yes. Okay, because actually, and it's even, I mean, like, it's even if you ask for more complex thing, that what is the color, I don't know, of the traffic light, for instance, it will consider that there is a traffic light, and so he will try to find the color, whatever the things. Okay, you see, so it's really, I mean, like, depending on the type of question and the way that the question is tricky or not, but you can have some kind of yes, very and you can have very easy example or more tricky example. For instance, this is a tricky example. Why? Because this image is a street image. It's one image about streets. There are cars. There are many things. Okay, but it's an old image, and there is, so at that time there were no traffic light, also. Okay, so it's quite tricky because you expect to have, because it's a street scene, things like that. So you are very confident that certainly there is a traffic light, except if it's a very old image. It is the case here. Okay. And so it's the kind of example that we can say adversarial is an example. Of course, if I show you, I mean, like an image of a banana and I say, is there a traffic light? The system will be able to say, no, I don't see any traffic light around the banana. Okay. But in that case, it's more tricky. Okay. And so again, it's very interesting in that case to learn to, I mean, like to correct this kind of hallucination and to be able to be sure that you have, okay, at least less hallucination. In that case also, I mean, like if you ask for a lot of detail, I mean, like, this is very, I mean, common that the system at the beginning is not so bad, but then after, I mean, like you try to I don't know, over-interpret, I mean, like many details inside the image, okay? But if you then try to, if you add this kind of steering, learn before, you really, I mean, like, are able then to focus really, I mean, like on many details that are really inside the image. Okay, so I think it's yes, it's more or less, I mean, like what I want to say for today, and of course we can, I mean, as future work or the things that we are working on at the moment are also how to use these kind of things in a more tricky, I mean, like hallucination context, as I say, for images, or also to see how to analyze, I mean, like this kind of big models when we are interesting, for instance, for robotic application. So what is the impact of steering for the action if we want to use this kind of model? All right. Okay. Thank you very much.